Welcome to the reunion workshop where we're going to hear the recent developments about Resurgent Asymptotics, especially the developments that happened since our 2017 KITP program. So the workshop will take place today and tomorrow. We'll have one session in the morning, one session in the afternoon, California time, of course. And all talks will be recorded. This one is already being recorded. Also, each talk will be 40 minutes long, and there will be a 15-minute time for discussion afterwards. So I would generally ask you to try and keep the questions for that 15-minute discussion. And also, I wanted to ask that if you do have a question, please use your virtual hand on Zoom and raise the hand so I can know that you have a question and I can announce it. I think that is all, and right now we're pleased to have Maxim Kontsevich talking about linear resurgence and topology of Lefschetz thimbles. Thank you.
Okay, thank you very much. Yeah, so I apologize for the people who listened a similar talk of mine almost 2 months ago, but there will be some development in that. Okay, so I will talk about Borel summation of four integrals depending on a small parameter when put one over small parameter in the exponent. So what is mathematical data here? We have a complex manifold of certain dimension n. At some point will be infinity. Then we have a holomorphic function, and anticipating Borel summation method, I will understand as a map to C, which C is a Borel plane, but it's just a function. Then we have a top holomorphic form, top degree holomorphic form, which is in local coordinates some function times dx1 dxn, and we get some closed n cycle, which is non-compact, but it goes to infinity in the direction where real part of function is goes to plus infinity. One can generalize it, and it will be immediately on this page, to the case when the cycle is not closed, it has boundary on some holomorphic divisor D. With the same property, it's still non-compact and goes to infinity. Then one can write the following integral depending on a small parameter, which I having in mind physics application denoted by Planck constant, just h bar, which will be for me a very small positive number. I integrate all my cycle, exponent minus function divided by h bar, and multiply by my volume form, and so I get a number if everything is okay and convergent. Yeah, and we can study in physics like asymptotic expansion, but also exact value. So asymptotic expansion and h bar equal to 0. Here's the kind of the most archetypical example. We take something called exponential integral in standard tables of integrals, E1, 1 over h bar, which can be rewritten in the form is convenient for us. It's integral from 1 to infinity of kind of we do not change cycle of integration depending on parameter but exponent. Exponent minus x over h bar, and the density will be dx over x. And then it's very easy to make asymptotic expansion. Essentially make a Taylor expansion of 1 over x near point 1. And then from this you see the asymptotic expansion will be exponent minus 1 over h bar is coming from the yeah, so you get this formula, and for exponent you get sum over asymptotic series, which will be definitely divergent because this term goes like it is n factorial in fact in this case. Up to sign. Now, so that's a basic example. And now I will just explain you that the Borel summation it's tautologically gives a right answer, so the actual integral. If you start with asymptotic expansion, how you get actual number. Now let's just choose a cycle of integration such as projection is a straight ray on a Borel plane, static at critical value and going in some direction which is not necessarily horizontal but goes to the right, and in such ways there's no other critical values on this integration cycle, on this straight ray, because anyhow, there are only countably many critical values. Yeah, so so we get a non-compact cycle, and which projects to array, and that can be thought of as a one-parameter family of compact n-1 dimensional cycles in fibers. And we get family of cycles in fibers for non-singular value, z not equal to z critical, and we can see the limit when z goes to z critical, and will be a class in homology of singular fiber, then the limit will be 0, and it's called vanishing cycle. So you get like small rate approaching singular value, and limit of homology classes is 0, because homology group of the special fiber is smaller. Okay, so now we can write integral in we can integrate first along fibers and then along the ray. So the integral is equal to the integral of gamma as exponent minus f of h bar. And then we can have this common factor, the critical of h bar. And then we integrate function of the ray, which is essentially coordinate on the ray divided by h bar, times the volume of the fiber. And when the volume is the integral of this n-1 dimensional cycle of n-1 form, which is quotient of mu divided by df. It's well-defined n-1 form on a fiber. Okay, the volume of the fiber is something like multi-valued analytic function, and you can go in all possible directions, and it has convergent expansion near the critical value. In the case when the monodromian homology is semi-simple, which is the following: it's certain sum of our rational numbers, strictly positive rational numbers with the same denominator, depending on the order of monodromia. Z minus z critical to lambda minus 1, some coefficients. Yeah, if the monodromia is not semi-simple, we should add also some powers of logarithms. But we do not meet it in my talk, so let's do it just rational powers. The volume is very simple function, and if you it's just convergent expansion, if you integrate, make a Laplace transform, you get same coefficient multiplied by gamma function, so you get inverse Borel transform. So tautologically, if you make from the right hand side Borel transform divided by gamma function, you get original volume function, and this function emits endless analytic continuation, because it's you can move cycles of integration, at least not break situation, as far as you wish, if you avoid singularities. And tautologically, if you move along this ray, then you get actual integral of this cycle gamma, which projects to the ray. Yeah, so you see that this Borel transform is kind of tautologically designed to capture actual integrals for integrals of this type, function of h bar times some density. Yeah, so what is the usual kind of proposal? How you do Borel summation? You make Borel transform, you make endless continuation, you have continuation along the path, and then integrate with exponent back, and you get your value. What I want to propose in the next slide is some alternative for Borel summation. You don't use this endless analytic continuation explicitly, but instead what you do, you use asymptotic expansion of integrals near all critical points, not just one critical point which you start with, but all critical points, and together with certain Stokes indices, which are integers, and equivalent to the monodromy data for the local system of, sorry, it's misprint, n-1. It's n-1 homology of the fiber. You can reconstruct your actual value without doing this Borel transform magic. So how we can do it? Let's assume, just to simplify the life, that all critical points are isolated and non-degenerate in the holomorphic sense. So it means that the Morse in holomorphic sense, the first derivative is 0, but second derivative should be non-degenerate quadratic form on the tangent bundle. And by holomorphic Morse lemma, you can locally make a function equal to constant plus sum of squares. And finally, I assume that all critical values of my functions are pairwise distinct. Then for each critical point, because this equation looks like sum of squares, you can see what is vanishing cycle, sum of squares in real numbers, so you get real square. So this vanishing cycle is diffeomorphic to n-1 dimensional sphere. And the only ambiguity, you have to choose orientation of this class. Now, if we have any more critical point and a generic direction, so the ray emanating from this point will not meet other critical points, then we define a Lefschetz thimble, which is a continuation of the vanishing cycle, kind of family of small spheres near your critical point along the path. And when I approach critical point, this spheres collapse. So it looks like a radial family of spheres, and the whole Lefschetz thimble sits just copy of Rn, diffeomorphic to a copy of Rn. And as I said, it's ill-defined only if you start your ray and meet on the ray another critical value. Otherwise, up to homotopy, it's well-defined, and you have well-defined answer. And now we define the following thing. Now we start to rotate Planck constant or small parameter at bar. So it will be some just non-zero complex numbers, not necessarily positive. And we have critical point. What we do, we draw a ray, so the point in direction which is equal to argument of h bar. So the exponent minus f of h bar will be rapidly decay along this ray. And if it doesn't meet any other critical points, we can make this Lefschetz thimble. And we integrate over Lefschetz thimble and make a normalization, just first cancel the critical value, expand the alpha of h bar, and also usually you next term will be Gaussian integral, and it will be determined, but also be something depending on h bar, 1 or 2 pi h bar over n over 2. So we get something like a constant. This will be square root of determinant of matrix second derivative. And by general theory, this thing will have asymptotic expansion just in non-negative integer powers of h bar. And coefficients here do not depend on direction, because it's kind of formal calculation. You can do it as, like using Feynman rule, for example. Write a function as a quadratic term plus higher order terms. Yeah, so you get this canonical series depending on only on the critical point. But this is, we have actually actual function, not only asymptotic series, and it's defined outside of Stokes rays when we get the directions, and so we get finitely many sectors if we have finitely many values. But this function extends analytically a little bit across the cuts. So you get just several functions on each sectors, but they have the same asymptotic expansion. Now, let's consider a direction which is kind of bad. So it means that if we consider a oriented line with slope theta, then we have at least 2 distinct critical values on this line. Maybe there are several of such lines, I could fix just one of them. So on one line, I have several critical values, alpha 1, alpha 2, alpha k, and I order them along because this oriented line. And now if I rotate a little bit direction theta, then the normalized integrals are well defined for all this thing. And there is a jump formula. If you rotate anti-clockwise, so increase values of theta, so you get integrals, you get certain function which you can eventually evaluate at OH bar, which is exactly on the direction theta. So we get a vector of functions, and we have another vector of functions on rotate clockwise. And the claim that they are related by upper triangular matrix with identity on the diagonal and exponentially small off-diagonal terms. So exponentially small off-diagonal terms will be certain integers depending on alpha to critical values lying on the same this line, multiplied by exponent of z b minus the alpha oh bar. It comes exactly because of this normalization. You see that here I use in the previous slide I use normalization exponent the alpha oh bar. The previous factor doesn't depend on critical point, so this will this is the origin of this factor. And the integer it's just says that it's homology class of the cycles going in direction theta plus is some linear combination of homology classes of cycles going in direction theta minus. In particular, the last one, the alpha k corresponding to the alpha k, the integral will not change. How to calculate these numbers? So kind of naively, one can say if you just with just two critical points, you count how many gradient lines for real part of your function divided by exponent minus e times e theta, goes from one critical values to another. But it's not really stable definition. And if, in particular, if you have several critical values lying on the same line, then one can shadow another, and you have trouble to define it properly. Kind of the most kind of correct ways to define these numbers is using one-carrier duality. You draw from one critical point this Lefschetz thimble, slightly rotated Lefschetz thimbles in direction very close to theta, but in rotating plus direction. But from another point, you just draw Lefschetz thimble in opposite direction, and they intersect. The projection intersect at one point, and in upstairs in your manifold, they intersect properly. And if you do generally, you get well-defined intersection number. So it will get some integer. That's a correct definition. Okay, so you get this upper triangle matrices. And now what we have? We have just a bunch of critical values. Okay. You have just a bunch of critical values and a bunch of integers for each pair of critical values. And these things will define a modification of the trivial bundle with fiber, this vector space labeled by critical points, over complex plane h bar. So it's not Borel plane, it's original variable. By gluing via linear automorphisms with the upper triangle matrices, or in general block upper triangle matrices, along Stokes rays. So at the end of the day, this I will be holomorphic section of your bundle. Yeah, so we kind of built our vector bundle by just gluing along cuts. And its Riemann-hilbert problem is to find a holomorphic trivialization of glued bundle. And there are many ways to do it. For example, Chikoty-Waffe many years ago developed some kind of good convergence series which will give you some solution of this Riemann-hilbert problem. It's not unique. There is a kind of very good holomorphic trivialization. The situation that this bundle carries a flat connection with second order pole, and one can try to find, for example, trivialization when the connection has second order pole 0 and first order pole at infinity. Something very familiar in kind of Gromov-Witten theory, this quantum connection. Anyhow, we can solve it one way to another, and yeah, so what's the Riemann-Hilbert problem in kind of plain terms of 19th century? Just to find matrix valued function, holomorphic function outside of rays, and which extend a little bit through the ray on each sector, and satisfying some jump equation on cuts. So you get function if you rotate anti-clockwise, clockwise, they're related by this out transformation, which come from this number z and n. And the initial kind of condition, which doesn't uniquely define it, it's a limit at 0 should be identity matrix. Yeah, so that means to solve Riemann-Hilbert problem, to find this collection of functions along outside of cuts. But then if you kind of normalize, divide by this G on the left, our vector of normalized thing, obviously we'll have trivial jumps because both G and I have the same jumps. So this comes. So we get a holomorphic function, holomorphic vector valued function. And let's try to calculate its Taylor expansion. It's a product of Taylor expansion of G, which is some question related to this number Z and N. We can extract this what is Taylor extension of G, and multiply Taylor expression of N normalized, which is something again divergent, but we can calculate using Feynman rules or whatever, this perturbation series. So we get two divergent series, one of in matrices, one in vectors, multiply them, we get form power series in vectors, but this is converged because our object is holomorphic. So we can evaluate it at some point if you, actual point if you want, and then multiply by G because it's also something explicit, and we get actual value of I normalized, actual value of collection of intervals. So you see, we don't do any holomorphic analytic continuation at all here. It's really different methods, and I think it should be used in resurgence theory, kind of in practice, not only in theory but in practice. Okay. Now I'll just go a few examples. So already in my first page I have an example of exponential integral. One can also, there's very similar examples of error function. But essentially any function which you find in standard big books of special functions has asymptotic expansion, which can be understood through this technology. For example, airy function is literally almost literally the same thing. So my manifold is complex line. Function is x group over 3 minus x, and measure is dx. So there are two critical points, plus and minus 1, where derivative function is equal to 0. And we get two critical values, minus 2/3 and plus 2/3. And you see that on the left on my screen, I just draw this Z1 and Z2. Z1 is on the left, Z2 on the right, just to keep it to you picture how it looks on the Borel plane. What I claim here is that Stokes indices are just plus minus 1 depending on the order we go from 1 to 2 or from 2 to 1. So in this example, one can see explicitly everything in terms of special functions. So there are two normalized integrals coming. You start to draw ray emanating from Z2 or from Z1. Let's start from Z2, because from Z2 we can start ray in any direction except negative direction when we meet Z1. And so on the complement to negative numbers, we get function I2 normalized, which after a little change of coordinates in the integral can identify with the airy function. Airy integral is integral of cosine Fourier transform of the exponent of I times t cube over 3. Up to certain rescaling of variables, you get this airy function, and it has a asymptotic expansion, which is given by this series of double factorials, blah, blah, blah. And Stern goes like n factorial. Because double factorials, something like or go half, so 6n goes to 3n factorials, by 2n factorials, you get only 1n factorial. Okay, so that's one function which defined associated with Z2 and defined in some sector, another function associated with Z1 defined in the opposite sector, and it turns out it's up to sine and some constant I, it's essentially the same function. And now, what are jump formulas? If you, for example, jump along function I1 when h bar goes a little bit above and below the positive real axis, the jump will be exponent times function I2 times this coefficient plus 1, which is integer, which is n1, 2. And similar in other direction, you get minus 1. Yeah, so it's all pretty simple. And one can also analyze Bessel function of modified Bessel function of second kind. There are about 6 different notations for different types of Bessel functions. So I use only one of them, K0. My variety is C star with coordinate x, so C minus 0, functions x plus 1 over x, measures dx over x, and critical points again plus minus 1, critical values again minus 2 and plus 2, so one can use the same pictures for area function, just change scale. And here the only difference is that stock synthesis are plus 2 and minus 2. It's explained why area and Bessel functions are so common functions, because it's kind of very basic example. We have just 2 critical values, and if it's a situation without boundary, we get skew symmetry. So that just 2 simple numbers, 1 and 2, come from area and Bessel function. And again, you get this asymptotic expansion, these factorials. Yeah, one can actually do as an exercise integrals with when you get cycles with a boundary, like exponential integral or error function. And then one gets something like n12 equal 1 and n21 equal to 0 for exponential integral. It's kind of not strictly skew symmetric situation, because this are some cohomology with some relative cohomology. Okay. Yeah, so one can understand this classical special functions through this picture. But also very classical function is gamma function. It's also can be understood in this way, but this is a situation slightly non-algebraic when we can have infinitely many critical values. So my variety is against C, but function is exponent x minus x. And measure is dx. It's algebraic measure still. But function is not algebraic at all. What is nice, the function is, if you shift variable by 2 pi I integer, the function will be shifted by, again, by 2 pi I integer. And it will play a certain role. So what we see, this function has infinitely many critical points. Just write what's derivative, exponent of x minus 1. So it means that you get 2 pi I times k. The k's integers are all critical points. And critical values will be 1 minus 2 pi I k. Yeah, so you get infinitely many critical values. But I claim that normalized integral is kind of the same for any critical value. It doesn't matter which one you choose of them. The reason is the following. If you go from one critical point to another, you shift your variable, it doesn't change measure, then the function will be shifted by constant, but in the definition of a normalized integral, I kind of cancel the constant. I cancel the critical value in the front. So it will be the same at the end of the day integral. So I get just the same integral, and which I calculate for k equal to 0, which is most convenient here, and I consider now h bar will be a positive number. Yeah, so by definition is given by this integral, exponent 1 over h bar, coming from this cancelling the critical value, 1 over square root of 2 pi h bar integral. Now make change of variables, exponent of x denoted by t, and I see up to some, again, rescaling gamma integral. Yeah, so get values of gamma function 1 over h bar multiplied by appropriate factor, so it should be very close to 1, and h bar goes to 0. One can also calculate integral in negative direction. It's very similar to the area function. You get essentially the same function, but now we get 1 over normalized integral. It's not minus normalized integral, it's really multiplicative. It's again doesn't depend on level k. So and asymptotic expansion, it's Stirling formula. It's how gamma function looks with this main gross term, and the remaining is 1 plus 1 or 12 and so on. And these are not Bernoulli numbers. For Bernoulli numbers, resurgence is much simpler, but these are exponent of series of Bernoulli numbers. But the resurgence somehow immediately follows from this picture. Kind of nothing to prove. And what here goes on? As I explained, there are essentially 2 functions. When we go to h bar has positive goes to real part or negative real part, and indexes doesn't matter. So I get two functions which I just reproduce for you. Again, on the right plane, on the left plane, and then we can cross array I times positive numbers or I times negative numbers, and get we cross all this anti-clockwise, and we get some transformation formulas which are very simple. So for the ray going up, we see I syncing it to the left, which we obtained. It's out on the right multiplied by 1 minus exponent of 2 pi over h bar. We can write it this IR plus minus 1. But here you see that IR was actually coincide with value of many integrals ik, and one interprets something like ak, another ak plus 1. So then it will fit to the general framework. Yeah, and similarly, if you go on the ray going down, you take divide 1 over 1 minus exponent, make infinite sum of arithmetic progression, and get again sum of plus ones. And so you see that get stock indices now depending on two integers, k and k prime, because my critical value is labeled by integers, and they given by this formula. It's minus 1 and plus 1. Okay, yeah, so it was really simple exercise. Now I go to actual kind of first physics example for resurgence. Let's start the usual path integral with Dirichlet action. So we have some remaining manifold with some, but for my purpose, its matrix should be kind of nice, should have complexification. And we fix 2 points and consider a space, X will be space of paths connected to my points. It has a real contour path which goes in a real manifold, and the actions Dirichlet action functional, which will be complex value to consider path and complexification, and we integrate exponent minus s times whatever Lebesgue measure with respect to holomorphic volume form. Yeah, so it's a fictitious object, but mathematical interpretation is a hit kernel when time is, and one should interpret a Planck constant as a time in this situation. The reason is because if you consider the action is homogeneous in the time of homogeneity degree minus 1, and that's explained by its kind of linear in h bar, not inverse in h bar here. Okay, so what we kind of it's kind of stupid here to speak about Planck constant. We can speak about time. T is now time, and now I consider a short time asymptotic for the hit kernel. And again, it's a standard factor, and kind of something comes from large deviations. We go to distance, square distance divided by 2t. So it will be contribution of the shortest path, shortest geodesics, and then we get certain expansion in t. And conjecture this expansion has factorial growth, resurgence, and Borel singularities has squares of lengths of complex geodesics, not real geodesics. So this the first example when it really works, and we see really complex geodesics. Real geodesics is hyperbolic plane. Take 2 points. There is only one real geodesics, but a hyperbolic plane like a sphere of imaginary radius, and then consider lengths of complete geodesic, you get to lengths 2 pi I n times go around this imaginary equator, and you get these complex numbers, and altogether you get numbers which lie on a kind of discrete points on a parabola in a Borel plane. And there was a formula discovered 50 years ago in this form, which you can see that in the integral you integrate something which can be understood as what you rate, you have a square root of certain entire function, because cosine is even function, it's entire function. It's a polynomial of infinite genus, so you get something like hyperelliptic curve of infinite genus. And this will be our manifold. Yeah, so it's pretty mysterious and works for other nice examples. So do you hear me? Hello?
Yes, yes.
Okay.
I can hear you. Just
Yeah.
one thing, you have just slightly more than 5-7 minutes.
Okay, I'll try to be.
Is that okay?
Yeah, so it's all works in many examples of explicit metrics, but there's really no pure kind of intrinsic mathematical definition through measure theory, Braun and motion. It's kind of through explicit special functions. The proof is not really understood here, I have to say. Now I go to kind of main bunch of examples. This will be 3 examples which should give this, I think, conjectures should give the same class of the data as critical values and Stokes indices. They're related with physics in dimensions 3, 1, and 0. So 3 dimension in all situations, my manifold will be infinite dimensional except the last case will be z car of another manifold, and another manifold is easy to describe. Like in 3-dimensional case, we consider gauge some bundle connections in complex bundle, let's say vector bundle, up to gauge equivalence, and there's some infinite dimensional manifold. In 1-dimensional space, we do the following. We have a torus, C star to power 2n, with symplectic form d log z I, d log z n plus I. And we took 2 Lagrangians, which are very special. It's called K2 Lagrangians. I'll give you example in a minute. There's a formal definition. If you know what is K series, there's something called thimbles for invertible elements. It's something called K2. We have this vanishing. But really, it's pretty explicit meaning of this. And in the third example, x0 is covering again some nice manifold x0 prime. And x0 prime is ZM cover of torus, now not even dimensional, but arbitrary dimension, minus some bunch of hypersurfaces given by monomial equal to 1. Just some bunch of hypersurfaces. Okay, now I explain case by case what is this section. So in the case of connection of 3 manifold, this section is a Chern-Simons section, and ambiguity Chern transformation is 2 pi L square z. So I go to smaller subgroup preserving this ambiguity. That gives me a covering. And as we know after Witten, that for special values, quantized values of Planck constant, we have a kind of compact cycle on my smaller manifold on this quotient, and when try to make integrals and get quantum Chern-Simons theory. It's completely formal for me. So the second case will be very brief. It's about this K2 Lagrangians. The basic example of K2 Lagrangians is the following. So we have the standard symplectic form on torus, and on each conjugate pair of coordinates, you put this kind of second coordinate is equal to 1 or 1 minus zi as you wish. So you get a bunch of possible K2 Lagrange manifolds. But then I can apply as monomial transformation preserving symplectic form, get really many Lagrangian manifolds, and try to draw paths from one to another. So another property of K2 Lagrangians, if consider disk with a boundary on the Lagrangians, then the area will be proportional to pi square. And the functional is again defined by integrating of 2 form. For example, if I have 2 closed paths, then I integrate to form over foregone spanned by these 2 paths and some paths in Lagrangians. So I will not develop on this more. And this case of dialog is again very simple. You have a subset of lattice minus 0, and it's with certain non-zero integer weights, and some even quadratic form. So what you make a multivalued function. This is just integer linear combination of diagonals of monomials, and some bilinear combination of logarithms variables. Dialog is ramified at 0, 1. You get many branches. And this differential, you can write as differential. And differential is defined on certain ZM cover because each coefficient of this of d log xi, it's certain integer combination of logarithms. It's logarithm of some algebraic expression. So there's integers labeled the choices of branches of logarithms, and you get this cover. and on another Ricardo you get function, not just one form. Yeah, so what goes on? It's very nice that in all three situations, these critical values of my function is just finite union of arithmetic progression with step 2 pi I squared, which is close to -40. So you can organize a certain finite group surrounded by this yellow circle and by integer shifted by this 2 pi square. Why this? And what are these numbers? These things correspond to some algebraic numbers eventually, because in three-dimensional case, critical points are flat connections, the same as homomorphism fundamental group to some matrices, and this is a bunch of algebraic equations over rational numbers. And for this Lagrangian varieties, they should be defined over rational numbers, which an example which shows that. So intersection, again, bunch of algebraic equations. And in case 0, if you write exponent of derivative is equal to 1, its actual exponent of derivative will be algebraic expression as well. And it's easy to see, but one should know a little bit case theory, is that one gets the same class of critical values. It's some infinitely generated abelian group, the image of Borel-Bennetson regulator, what is called. It's some huge things of size of essentially half of algebraic numbers. Yeah, so the big conjecture is that maybe it's true, maybe not, that one can identify the situation in different functional dimensions, not only matching critical values, but also the stock indices, which eventually define to you the whole this Riemann-Hilbert problem. And if you get this, and in all the situations, because the whole things can grow to by parallel paths, all rays will be approach horizontal ray, one can make kind of like infinite product of half of this infinity of rays and get some one transformation. And in Riemann-Hilbert problem, we just replace infinitely many cuts by one cut. So it will be eventually important to just calculate just two transformations. And now I will show you some calculation which I've done just in last few weeks, 2 weeks. I'll start with some ad hoc example. And the last page. So it will be zero-dimensional case, the case when I can really calculate this stock synthesis. I take a function just out of blue, del log of x plus 2 times log x squared, just not one to be more interesting. So my variety x0 prime can be written as some in this form, as you take x not equal to 0, 1, and x power 4 minus x, take a logarithm of it, call it t. And we get to map phi from x0 prime, which variety to c star. Yes, it's ramified. You get something like infinite cover, and ramified at 6 points. First, it doesn't take value 0. It's the mononomial around 0. It's not trivial, but also there are 4 points. Namely, solve equation x power 4 plus x equal to 1. I get 4 solutions. Apply this function f. You get 4 points, 2 of them lie in the circle, unit circle 2 do not lie. And also you get something like missing eigenvalue because x equal to 1 is excluded from this story, but you can substitute to the thing, you get pi square over 6, and you take exponent of the guy, you get exponent minus pi I over 12. You get some missing kind of new point, it denote theta, whatever. So I choose some base point and using, and I calculate what is the fiber, and fiber turns out to be labeled by integers multiplied by index from 1 to 7, so I do not integers and index from 1 to 7. And I calculate monotomy anti-clockwise. It's pretty nice from t, it's shift from index, t1, t2, t3, t4, it's just involution, permutation of two fibers because it's kind of double ramification point. But monotomy around to sit, it turns out it's fix all points in the fiber except one semi-infinite, two-sided infinite cycle, which is kind of pretty complicated picture, but it's a very regular one. You see, you can repeat kind of indices repeat 1, 2, 3, 4, 1, 2, 3, 4, and so on. Then start to 5, 6, 7, 5, 6, 7, 5, 6, 7. And integer index relies to some quadratic progression, I would say, kind of value of some quadratic polynomial. Like for low index 1, you get 2n squared. And can, from this data, you can reconstruct all things from everything. So it remains something like theta function. But I have to say I'm really at loss what to do with this, because this mononomial procedure, we get infinite Jordan block, and in the expansion of integral, I get something which we'd never see it in, at least in this Chern-Simons story, exponent of integral of y times y over h bar. It's some strange asymptotic related to maybe a Lambert function. So something is wrong here, but I don't know what to do. Okay, thank you.
Thank you, Maxim. Thank you for the very nice talk. So we should start the discussions. I can already see that Ovidiu Costin has raised his hand. So
okay,
I will allow you to talk, Ovidiu. You have to unmute yourself.
Okay, can you hear me?
Yes.
Yeah, maybe should I share a screen? I can stop.
Perhaps keep sharing the screen. It might be useful.
Okay.
Yeah, I find this alternative to Borel summation extremely interesting and nice. And I have a couple of questions, but first of all, does your method depend or require an integral representation of the function?
Yeah, yes. Yeah, no. I just say it's kind of, in the sense of tautology, if you have, not tautology, I have to say that this endless continuations should come from a kind of Gauss-Manning connection. That's the message.
So, for instance, it wouldn't apply for a non-integrable ODE, non-linear.
Yes, yeah. No, this is actually an interesting story. Actually, I call this whole story linear resurgence because I glue bundle by linear transformations. And if you go to things like WKB, you get non-linear transformation, but the same scheme in a sense.
Because indeed, if it generalizes, then it would be a powerful tool. I mean, it may replace, say, Ecalle acceleration, which is a very onerous and complicated process when you have multi-summability.
Yeah.
Yeah, so that's
yeah. No, in a sense, one can. There's a case, for example, of Ecalle-Varonian theory. It fits very well to kind of non-linear generalization. It's kind of just a tautologically one-dimensional case of this, but.
Okay, thank you.
So we have another question from Jan Soibelman. Now you have to unmute yourself.
Yeah, okay, thank you. Do you hear me?
Yeah, can you be louder?
I'll try to stay as close as. Yeah, I have two questions. One about your last slide. Since you said that it's asymptotics which you didn't see in complexified Chern-Simons, if there is nothing wrong, does it disprove your conjecture that 3, 1, and 0 are the same?
No, in fact, I have the following idea. It's maybe I have this infinite rank local system, with kind of rank monodromy around one point, get infinite Jordan cell. But this example is not really related to any three manifolds. And maybe for realistic example, one can make a quotient of the system, so the monodromy will have finite Jordan block with some eigenvalues.
Yeah, but the differential is K2 Lagrangian. Am I wrong?
Sorry?
Differential of your function, it seems to be in the class.
Oh, yes. No, of course it's a differential function, K2 Lagrangian, but it's how it meets with this Lagrangian manifolds as well, Yeah,
and I have a second question, which kind of maybe completely stupid. You use a geometry which is kind of C star. Can you replace it by elliptic? I mean, at least the case 3 survives. I don't know what's happened with the other.
Yeah, it's interesting question. I don't know.
Yeah. Okay. Yeah, thank you.
Thank you. So we also have another question from Marco Gualtieri. You have to unmute yourself.
Oh, okay, thank you. Could you go back to the slide where you talk about the complex geodesics?
Okay, yeah, no problem. A second. Yeah.
Okay, so
this one or previous one?
yes. No, this is right. So you have this infinite set of critical values.
Yes.
And this is in the Borel plane. Your parabola is in the Borel plane.
Yes, exactly. Yeah.
And so then, if we want to understand the singular directions in the H-bar plane, we should look at all pairwise
differences. Pairwise difference, exactly. Yeah.
Yes. And so we'll obtain a sequence of bad rays, which is similar to your picture of wall crossing, right? In the next few slides.
Yeah, but in fact it will be because it's 6 of infinite rank, you get bad rays, I think, dense in every direction at the end of the day.
Oh, I see.
Yeah.
So then, okay, I have maybe in that case, my question splits into two. So if you had rays which were only accumulating in one direction, then is my understanding right that we could use your formula in order to remove that infinite set and replace it with a single line?
No, there are two different issues. Here there's a problem that we have infinitely bundle of infinite rank, which is again a bit unhealthy mathematical object. But even in some situations when we have there is a story about density of rays in non-linear wall crossing. They could be dense everywhere, but there we still get transformations will be diffeomorphisms, not linear transformation of some finite dimensional torus. And one can arrange this infinity of cuts, just organized in several groups, infinite groups, which are contained in strict sectors and multiplying along the sectors. So eventually can go to 2, 3, 3 will be enough for any situation, finite transformation for your Riemann-hilbert problem.
And does that not work for the linear case?
It also works for the linear case, but this additional trouble is that you should get infinite rank bundle. But,
I see.
Yeah, what can do here? Three directions. Yeah, I think it's.
So you're saying that even here where it's dense,
It's okay. Yeah, it's okay. You just multiply infinitely many things in the same angle sector. It will be still something defined in this.
Okay, but you haven't explained in your talk how you know what that formula says. It's your previous work, right? The wall crossing formula.
No. It just multiplies all of them in clockwise order. Yeah, in the sectors. That's it. Okay. Yeah, same story.
Okay, thank you.
So, thank you. So we have one more question, which is from Sergei Gupov. I think you just need to unmute yourself.
Okay.
Hello, Maxim.
Hello.
Thank you for a very nice talk. I have a question about last part where we have infinitely many critical points. And you have this, actually this slide. So in the bottom, we have this map from K-theory. So I was wondering what would happen to this part of the story in the presence of boundary that you mentioned much earlier.
If you have a boundary, so it means that you have kind of like integral depending on parameters, yeah? So this point should start to move.
Perhaps something like this, or
I think you get not just constant, but things depending on some auxiliary parameters. I don't know what to say. One can like in Chern sense, one can put some boundary condition depending on continuous parameter.
Yeah, I guess the question is if any part of the K-theory survives or becomes over function field or something like that.
Yes, it will be over function field. It will be. For example, this Lagrangian K2 Lagrangian manifolds, which I considered before, you can shift by some constants. We can make multiplicative shift. And then the integral will depend on these parameters. Okay?
Yeah, thank you.
Okay.
So, sorry, I think we have time for a couple more questions. I have one question, and Marcos Marinho has also one question. Marcos, I think you need to only unmute yourself and you can ask.
Yeah, hi, Maxim.
Hi.
I wanted to mention that actually in work we did with GEU and Stavros Garoufalidis, which was published today, we actually computed this Stokes constant for actual complex Chern-Simons theory. So I will talk about that tomorrow.
So I didn't study yet your paper, I have to say.
But we have explicit values for all these Stokes constants. So.
For me, I think I also can get everything, but what worries me is the stupid critical values which behaves kind of wrong way.
Mm-hmm.
That's it, yeah. Okay.
We had, a question about just what do you mean? Can I quickly ask one question? What do you mean that the I is an alternative Borel summation?
Because the calculation should be done in a different way. So somebody should calculate all critical values. So imagine like you want to calculate standard model results. You should have 4 groups of students. One calculate critical values, complex critical values. Another calculate this as integers, Stokes integers. Another person calculate perturbation theory up to 5th order, whatever in your points. And then another person write a program how to go from this integers and complex numbers go to actual solution of Riemann-hilbert problem. So, so it's completely different. 4 different tasks when together gives you actual number. It's very good precision. Yeah.
Thank you. Just one thing. So we have if it's a very, very quick question, I think we have Alireza Betash that also would like to ask a question. You can unmute yourself, but I would ask to be very quick.
Yes, I will be quick. So what can you say about the, degenerate fixed? I mean, if I have, so obviously you have talked about some assumptions in the beginning.
Degenerate, critical points.
Yeah,
it's not
what
a big,
can you say about that?
Yeah, it's not a big deal. Yeah, one can replace by something like vanishing cycles and the gluing, and this things is replaced by some kind of gluing data. But
so your formalism still will apply?
Yeah, everything will work. Yeah, it's really not a big deal. Yeah, and then at the end you get again vector bundle with some connection, second order pole, and so on. So it's, just for brevity, I go to this simple case.
I'll have to say so. Thank you, Maxim. We have to go.